So another form of approximation is approximating with differentials. But it's important to understand that there are two types of differentials. dy, which is the rise of our tangent line, and delta y, which I remember is change in y values. So let's look over here to the left to see what's going on. So we start at some function, at some x value. And instead of only going up the rise of my tangent line, I am going to follow my curve all the way up to this y value here, which is going to be f of x plus delta x. So between those 2 points, we can draw our secant line. And so this is the secant line. So the slope of that secant line, let's see, it seems like I go up, I rise, and I run. Now what is my run? My run is the same run here. Delta x equals dx. But what is my rise? Now let's see, what is this value? This y value is the same y value here, f of x plus delta x. So the rise of my differential here, delta y equals f of x plus delta x minus f of x. So the difference is we are using the slope of our secant line here. The rise is delta y, and the run is delta x. So we remember that even though delta y and dy are generally different, for very small changes in x, they are good approximations of one another. So here's our tangent line, our secant line. They're pretty good approximations, pretty close to each other around this x value. So the main summary is delta y over, delta y over delta x is approximately the same slope as dy dx. That is, the slope of our secant line is approximately the slope of our tangent line if we look at those pieces as differentials. So now we have to figure out how to find delta y. Well, we already discussed that up top. Delta y is change in y values. So delta y is f of x plus delta x minus f of x. That's that differential. Now, how to approximate using differentials. And I want you to show this work every time. Okay, so we are going to show this work every time so that you show me and you show an AP grader that you understand what a differential is and how to derive its linear approximation. So from above, we know delta y over delta x is approximately dy over dx. We can then multiply both sides by delta x, and I have delta y is approximately dy dx delta x. Now, don't forget that dy dx is just f prime of x, so delta y is approximately f prime of x delta x. But what is delta y? Delta y is f of x plus delta x minus f of x is approximately f prime of x delta x. So if we want to approximate using differentials to find f of some function close to an x value, I try to isolate this term here. So f of x plus delta x is approximately f of x plus f prime of x delta x, which you notice is very, very, very similar to our linear approximation function So that's why if I'm going to ask you to use differentials, I'll want you to start by showing this relationship first to show that you understand that you're using differentials, and then derive this formula and then apply it to the problem. Let's do an example next.